Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about normal quantile plots, or QQ plots for short. They will help us assess one of our assumptions, the assumption that the model errors are normal. Okay? Let's begin. The plan for this video is the following. First, we will learn how to construct QQ plots step by step. Then, we're going to do it using built-in functions from R. And finally, what we're going to be doing is a couple of simulations and see what QQ plots look like when the normality assumption holds and when it doesn't. Okay? Well, let's begin. So first, in order to learn how we can make QQ plots step by step, let me refer to our lecture notes. So we have a very small sample here with only 10 observations in it. What we did here is we ordered those observations from smallest to largest. Okay? So that's the first column. Again, they have been ordered from smallest to largest. Okay, now the second column on our table, right, is a modified empirical cumulative distribution function, if you will. Think about it. We have 10 observations. So if we were computing the empirical CDF, we would have 1 out of 10, that would be 0.1. We would have 2 out of 10 at this point, so 0.2, and so on. So it would be in general, for the jth observation, if it was the empirical CDF, it would be j over n. But we modified this one here slightly, so it's j minus 1/2, so it would be 1 minus 1/2, 1/2, or 0.5 divided by 10, 0.05. Makes sense? 2 minus 0.5 divided by 10, and so on. And then what we do is we find the quantile, or the critical value, if you will, from a standard normal, such that the area to its left corresponds to that number here. Okay? Make sense? So in this case, the area to the left of negative 1.645 is going to be 0.05 for a standard normal. Make sense? Okay, let's keep going. We need to launch R. So, as usual, the first step will be entering our observations, right? So let me call that guy, the object that we're going to create, ops. Let me use that C function that we have used before. First observation, -1, negative 0.1, 0.16, 0.41, 0.62, 0.8, 1.26, 1.54, 1.71, and 2.3. Okay. So now we need n, the length of our sample. In this case, it's going to be length of observations. N must be 10. We're good. And now I would like to create that second column. Okay, I'm going to call that prob, as in probability. Okay, so prob is going to be just, and note that one way of doing this, right, we know that it's going to be 1 minus 0.5 divided by n, right? 2 minus 0.5 divided by n, and so on. So what I'm going to be doing is, let me show you. I don't remember if we have already used this command, but if we haven't, let me show you. So we can create a sequence from 1 to n with a distance of 1 between each of the elements, right? Okay, so and then what I'm going to be doing is subtracting that 0.5, okay, and then I would like to divide that guy by 10 or n, because that's right, something that we already had, the length, the number of observations, the sample size. Okay, so now let me save this in that object I was going to call prob, as in probability. Okay, now prob contains what I want on the second column, right? Okay, now we need the third column, right? So those are the normal quantiles. Okay, so there's a function called qnorm that is going to help me find that. So for instance, if I want a probability of 0.5 for a normal 0, 1, right, and that's the default, as you can see, the mean is 0, the standard deviation is 1, so it's a standard normal, that's the default. We know that the quantile, the number from a normal 0, 1 that is going to have 50% to its left is just 0, right? Okay, so that's the function that we want, but we want that for these probabilities, right? That vector of probabilities that we created. So right, see, so these are more accurate versions of what I have on the third column of our table. Okay, let me save that in an object called norm, as in normal quantiles. Okay, now it turns out that a QQ plot is just you know, a graph of the normal quantiles, the theoretical ones, against your observations. Okay, so let's see. Plot norm quantiles against obs, right? Let's see what we get. So that's what we get. Okay, now let me make it look nicer, something like this, a little bit of bells and whistles. Let me add title, main, hours. Let me add a color, blue. I want solid circles, so PCH equals 19. And now let me just yeah, that's good enough. Okay, Make sense? Okay, so that's hours. Okay. Now, let me show you again. This is hours. Okay. See what it looks like. So here on the horizontal we have the normal quantiles. Here we have our observations. Now let's do it using R. Okay. So using R, you will use that built-in function called QQNorm. Okay. And all you need is your observations, and you don't need to order those from smallest to largest or anything, just as they are, right? And use that QQNorm function. Let me use the same color and also solid circles. See, this is ours. Okay. And that's what R does. Okay, here we have the theoretical quantiles, here we have the sample quantiles. Okay, make sense? So it looks exactly the same. That's ours. And that's using that built-in function. So the same thing. So now you know how you could create a QQ plot for normal distribution step by step, and it isn't hard, but now you are able to fully understand what QQ plots are doing, right? What is the information in that graph. Okay, so now next item in our agenda, we said that we were going to carry out a couple of simulations and see what happens with those QQ plots, see how they behave when the normality assumption holds and when it doesn't. Okay, so let's carry out that simulation. So first, let me create a vector with a bunch of numbers coming exactly from a normal distribution. So there's a function in R called rnorm, as in random normal variates, right? So let me show you first rnorm, and let me just create, say, 10 of them. We have two parameters, as you can imagine, mean. Let's do it with standard normals, right? The default would be 0 for the mean, standard deviation 1. So if I didn't do this, R would, you know, create those 10 numbers, those 10 random, would draw 10 random numbers from a normal with mean 0 and standard deviation 1, even if I didn't specify these. So it's just, you know, to stress that you could change these parameters here, okay? So 10 numbers, right? But we don't want 10. I want to create a lot more. Let me generate 1000 of these numbers, okay? And I'm going to assign them to an object that I'm going to be calling sim, as in simulation, okay? Okay, there we are. Now, we know that there's a built-in function to, you know, make a QQ plot. So let's use it. QQNorm of our simulation. Okay, let me add a main title to my graph. Call it simulation, and it's a normal distribution, right? Okay. Color, how about, I don't know, red? Yeah. Okay. Okay. So now it's always a good idea to add a line, because the thing is that you want to compare those points against what you would exactly get. Okay, so QQ line, that's how you're going to create that line. Okay, so even in this case, right, this is the ideal situation. That straight line is showing you what happens if things went perfectly, right? But it's just like when you're rolling a die, right? Even if you're rolling a fair die, say 600 times, you're not going to observe 100 sixes, right? So it's the same here. Even when the normality assumption holds exactly, because we are generating these numbers from a normal, right? There is some slight deviation with respect to that line, which is what the theory tells us. Okay, so anyway, some small deviations even when the normality assumption holds exactly. Now let's see what happens when it doesn't, when that assumption of normality doesn't hold. Let me now, instead of generating numbers coming from a normal distribution, let me generate a bunch of numbers, but now coming from an exponential distribution. Okay, we know from statistics 256, right, that exponential distributions have a single parameter, beta, right? So I'm going to make my life easy, and I'm going to use beta equal to 1, right? Okay, now let's do the same thing that we did before. Let me do a quantile normal plot, or QQ plot. And the thing is that we are using QQ norm because we want to see whether or not it is reasonable to assume that these guys come from a normal. So that's my second simulation, sim2, right? Now the simulation comes from an exponential. So let me remind us that exponential and beta is 1. Let me use a different color. How about green? Now let me add that line so can you see? In this case it is clear that the green dots are very far from the line, and that's what you would ideally see if you had exactly normal distributions without any variation there, right? So anyway, now you have seen what happens there. One more comment about that. So again, let me show you what we had before when normality holds exactly, right, for 1000. In that case it was 1000 observations, right? So the red dots are very close to that line, right? And that's what you would expect. But now let me show you what happens when the normality assumption holds, but you have a small sample size. Okay? So let me recycle what we had here. Let me call this guy sim3. And now let me generate 30 numbers coming from a normal distribution with mean 0 and variance or standard deviation 1. Okay, so now let's make that normal QQ plot. Let me use a different color. How about purple? let me add that QQ line. So, and you see that there's some deviation with respect to that line. There's some fluctuation, even when you know, these guys are exactly normal. And let me do it again. Another sample, another graph. See? Even when these guys, these 30 observations come from a normal, you could see some deviations with respect to that line that you would expect, you know, if they come from a normal. So anyway, the point being is that when you have a small sample size, it's hard to assess normality. Even, you know, if you had it, if these observations actually came from a normal, sometimes, you know, it's going to be hard to say whether they actually came from a normal. Anyway, just you have to be worried about this when there's a clear violation of the normality assumption, okay? And just bear in mind that by Gauss-Markov theorem, right, if you're just interested in point estimates, then you're going to be fine even when the normality assumption doesn't hold exactly. Because of that theorem, Gauss-Markov theorem, you know that they are the blues, the best linear unbiased estimators, right? But if you want to carry out hypothesis tests or find confidence intervals or prediction intervals, then normality is more important. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.